Edward. So today I'm going to talk about how Earth observation data and AI can be used in your industry and some of the things that we're doing in CeADAR with Earth observation data at the moment. So firstly, I'm just going to sort of give a background into AI sort of in more generally, which sort of paints a picture more specifically of how AI and Earth observation can be combined together. So when we think about AI technology, it's been advancing rapidly in recent years. So these are through things such as much larger volumes of data that's been available as more industries are digitized. There's more sensors out in machinery and in the environment, monitoring, recording data, capturing data. The variety of this data and the velocity, the speed at which this data is collected and recorded has been massively increasing over the last many years, number of years, specifically in the last 10 years or so. So this increase in data, combined also with advancing computational power, where we now have computational servers, we have data centers and these types of resources that are able to process and work with these large volumes and speeds of data. And we also have this combined with the algorithms themselves. So the machine learning algorithms, the different approaches to actually operate on this kind of data, making use of these advanced and higher performance computational capabilities. So these three aspects are the kind of key factors that have led to the rapid improvement and rapid advancements in artificial intelligence technology over recent years. But it's always worth thinking. I mean, AI is a word that's kind of bandied about quite a lot, but it's really worth thinking of what do we actually mean by AI. So broadly speaking, there's this general concept, artificial intelligence, and it's been applied to a lot of different things, a lot of different areas. Nearly every company you might speak to these days say they're doing AI and something, but what does that actually mean? And one of the areas in AI, machine learning, is what we really think about and what most people talk about in terms of AI currently. And within AI, there's also many other areas that can be considered artificial intelligence. So there's techniques and fields such as symbolic reasoning. We have expert systems. These were kind of AI systems that were the kind of latest cutting edge, maybe about 20 years ago. Now machine learning is much more taken over in the field of AI, but expert systems are still very much used in a lot of industries, and they very much still fall under the label of artificial intelligence. We have things like causal inference. So these are more maybe advanced techniques. There's not a huge amount of work. These aren't really applied in any industry settings. This is much more sort of research field still. And there's many others that encompass in this field of AI. However, within machine learning, this is really where the focus is a lot of times when we're currently talking about AI. And the big thing in this that we hear a lot recently is deep learning. So deep learning is a particular type of AI, of machine learning. It's a particular way of building machine learning models. And as I mentioned, machine learning and artificial intelligence, they're often used synonymously. And it's a useful kind of way to think at the moment, because being AI, this very broad term that can apply to many different things, a lot of times that just means machine learning techniques. And machine learning really is the sort of cutting edge in AI technology at the moment, particularly in kind of industry applications and how companies are kind of using this for sort of real world benefit and real world opportunities at the moment. So just a sort of overview of what we mean by machine learning. So this is sort of how we think of one part of machine learning, which is supervised machine learning, which is sort of the vast majority of how the models are used and built in industry. So with that, we have a set of labeled training data. So in this diagram here, you can imagine these as documents, for example, and you have some that might be, classified as sports articles, some as current affairs articles, some as as weather reports, whatever they are, these different labeled training data sets. And they already been labeled by human annotators or by some other source. Then you have a machine learning algorithm that processes this labeled training data and learns the differences between these different classes automatically of documents, for example. And then once you have a trained model that's been learned from the data set, that trained model can be used to infer, for example, the class of new unseen documents. So this machine learning model has learned from the labeled training data set. It's produced a trained model, and that trained model can be used then for useful things like making decisions around what kind of document it is, what the image might be about, what a particular piece of data might predict about an outcome, and so on. And in the context of Earth observation data, there's a number of particular techniques that have been used a lot for Earth observation type data. So I'm just going to go into that a little bit in the background so we can see then how some of these are being used. So an example of a machine learning algorithm, which is part of a deep learning type techniques, is called convolutional neural networks. So if we think of the previous diagram there, we see that the machine learning algorithm in the middle, in the case of deep learning and these convolutional neural networks, that's just, it's an artificial neural network, which is kind of based on the way we think human brains work, with different neurons that are connected in very complex networks. And just like in the previous slide, these artificial neural networks are trained on a labeled training data set. And then given a new example, the trained model, the trained network, then can make inferences and predictions and classifications of what it's being trained to do. And these convolutional neural networks, they're a specific configuration of these deep neural networks. And they're specifically developed to work on kind of 2D or multiple dimensional data that has some spatial relationships in it. And you can think of these, the classic example of this is in image object detection. So for example, when you have an image that's input into one of these networks in the training data, these networks are very much customized and built to be able to interpret that image data, that sort of 2D multispectral data, and to learn and train things about that data, such as recognizing whether they're pictures of cats or dogs or different types of objects within those. And these are suited for things like classification and object detection and many other tasks on image and image-like data. Now, where this is relevant to Earth observation is that a lot of Earth observation data fits into this type of description. So it's data that has been captured predominantly by satellites orbiting the Earth using high resolution sensors pointing down at the Earth. Now, we might be familiar with Google Earth and looking at satellite imagery. So these are just images of the Earth, of regions on the Earth. So as you can see, with convolutional neural networks, these apply really well to that kind of data. And there's also, as well as visual imagery, there's other sensors that look at other areas of the spectrum. So they might be looking at infrared. It might be radar, looking at the heights and the changes in height of areas of the Earth. There's other sensors looking at things like different kinds of gases in the atmosphere and on the Earth's surface, looking at temperature and so on. But these all fit into this broad kind of area of these 2D, generally 2D kind of maps of parts of the Earth, which very much fits into Earth observation data. And just to show the power of these types of convolutional neural networks, so this shows the progress in terms of image recognition on a very big reference data set called ImageNet over the last number of years. And this only just goes up to 2017 here. So this shows within that year, the state of the art on the benchmark, on this benchmark data set. And we see in 2010 and 2011, this is kind of just before convolutional neural networks and deep learning was really applied to this. And we're still over 25% error rate. So 25% errors on this benchmark. But then we can see as convolutional neural networks and deep learning has improved in more recent years, that's massively improved. Now, the actual human error rate is about 5%. So if you get humans to label what they think, you know, the objects are in these images, there's an actual general rate that humans would get of 5%. And now we're seeing some of these latest approaches improving over what humans can do. So it's better than sort of human error on these kind of tasks now. And these convolutional neural networks can be used very effectively for Earth observation data. So we see some examples of visual data here, where we have some examples of, for example, detecting aircraft on runways and on the ground. We can see automatic splitting up different boundaries of agricultural areas. On the right-hand side, tracking ships from satellite data. Some of the examples below on the bottom line are identifying different types of crops grown in different in fields, actually from that satellite data. So these kind of automated convolutional neural network-based AI techniques can do some really useful tasks using this kind of data, and it's improving all the time on what these can do. Another application using these kind of networks is called Superresolution, where you might have an original image captured by satellite, which the resolution mightn't be particularly high. It might be older sensors on the satellite. There might be interference in the atmosphere. And using convolutional neural networks that are trained on a large amount of data, they can actually improve the resolution of those images based on learning the kinds of features that are apparent in these kind of images. And this is hugely useful for sort of improving the quality of the images and the data that's actually been retrieved off the original satellite sensors. That's another huge area where CNNs have been applied. But just to go on, there's a number of challenges around applying these kind of machine learning algorithms in Earth observation data and also in general. So all these convolutional neural networks, deep learning approaches, and these general machine learning approaches need training data. So what this means is, if you go back to the previous slide where I showed that diagram, on the left-hand side, we have this training data set. So this is a set of labeled examples that you're telling the algorithm. This is an example of this type, for example. Or in an Earth observation, you could be saying, well, here's a load of examples of annotated aircraft in satellite imagery. So you're asking the algorithm now to learn what an aircraft would look like in many different configurations to be able to automatically detect that. But those labeled training data sets are usually very hard to generate. You often need people to do this, like there's people actually labeling these data sets. Takes a huge amount of effort, and a lot of these algorithms need really, thousands or millions of annotated examples. So this is really the bottleneck in applying these techniques. The algorithms themselves are fairly well understood at this stage. The computational power needed is generally readily available, but the labeled training data is currently bottleneck. And in Earth observation data, now there's a number of opportunities and solutions for tackling this labeled training data. So one way that can be done is using complementary data sets. So there's many conventional mapping data sets around, or existing graphical information system data sets that can be used for this. So you can combine these traditional sort of manually surveyed data sets and combine that with the satellite imagery to build and generate your own training set, then to train an AI machine learning based approach to then do that automatically in a much more efficient way. There's also an approach called transfer learning. So what this is where you train your neural network on a kind of more general data set. So in this case, it could be the ImageNet data set, the baseline data set I talked about previously. So these are very generic images in many different categories. I think there's over 1,000 different categories, for example, 1,000 different classes. But these might have nothing to do with Earth observation, the majority of these. Or in this image that you see here, this diagram, what we're doing at the end is actually there's a sort of specific fashion data set we're trying to find or be able to label different types of clothing. Now, the general ImageNet data set wouldn't contain many examples of different types of clothing. It's a very specific application, but you can train the network on this general data set, and then in the last layers of this network, you can just train it on a smaller set of the very specific data that you want to apply it to. So it learns the kind of general background and information it needs from these general images, and then you focus that in on the specific data you want. So you can do this with Earth observation type data as well. That's another way to improve or reduce the need of very specialist training data. And a third one, which is often used, is actually incentivizing people to help you. So we've all seen these kind of captchas where you're just trying to sign up to some online service and you get this thing to say, click all the parts of the image that contain traffic lights or bridges, or type the text of this kind of very fuzzy looking scanned piece of text. And what you're actually doing there, as well as it's checking that you're a human, because you're doing a relatively hard problem that in that particular case, a machine learning algorithm might be able to solve, but you're actually labeling that data, and they're collecting that data from all these thousands of people doing this to collect this labeled data to train and improve the algorithms. You might also see kind of citizen science projects like this. So the top right is a citizen science project where it asks people to label the examples of penguins in photographs. And then this is building up training data, and the labeled data then can be used to train models to automatically do that. And the bottom right as well is people volunteering sort of measurements and things that they view in their environment and labeling that. Then you can use that labeled training data. So there's a number of approaches to this training data conundrum. So I'll just very quickly wrap up now with some of the work that we're doing in CeADAR in applying AI and machine learning techniques to Earth observation data. So I suppose that it's true to say that there's many data analytics and AI techniques that they're not specific to a particular type of data or application. So a lot of these techniques that are applied on, say, structured data or on text data or time series data, audio data, for example, they can be also applied on Earth observation type data. So there's a lot of general expertise that we have in CeADAR that can then be applied on the more specific Earth observation type data, and we can leverage the expertise that we have in the center across all these different application areas. A number of those, for example, in previous projects that we've worked on is deep learning for opaque data, which looked at deep learning approaches for very complex types of data. This can be applied to Earth observation data from complex sensors, for example. Multimodal deep learning, which is looking at how you combine data from different types of sources and sensors of different types into a single model to improve your AI or your predictive capabilities. Again, this is very relevant for Earth observation type applications. Also last October, a team from CeADAR took part in the International Space Apps Hackathon, which was organized through NASA. The CeADAR team actually won the Irish event in that with a proof of concept called Lemonade, which was using satellite Earth observation data along with other data sources to help the refugee crisis. That was going on. The team are now going to go on to the next stage in the international competition on that. We're also working, and we're midway through a 6-month collaborative research demonstrator project, which is looking at applying AI techniques in general to Earth observation data. And we're currently working with a number of companies that are involved in that project that you see there. We're also starting, hopefully mid-June, a project on building specifications and best practices for AI-ready Earth observation training data sets. So this is providing standards for how you format Earth observation data with labeled examples to allow different researchers to use this data to build better models, and it's a more standardized approach to building these training sets. And we're working with iCheck, the Irish Centre for High-End Computing, on this project, and the project is for the European Space Agency. So we're we're going to be starting that in the middle of June. And just finally, we're very interested in partnering with companies to develop new and exciting AI-powered Earth observation-based applications for competitive advantage in your industry. And we think there's a lot of opportunities for industries and different companies to start looking at advantages that they can get through using Earth observation data in their particular fields, and would be really happy to help you work on some of those projects. So thanks very much. I hope that was it was a kind of a flying overview of AI for Earth observation, and I'll be happy to take any questions now if anyone has any specific questions.
I've got one question.
Go ahead.
Yeah, earlier you mentioned the training sets and how you can leverage the crowd through the penguins and stuff like that. Is there any commercially available product where you can do that?
So yeah, well, there's a number of well, they're more kind of specific projects for different kind of areas. So some of these kind of citizen science initiatives. In terms of general products, I mean, what people do quite a lot is use things like Amazon's Mechanical Turk, Crowdflower, and these other crowdsourcing programs that, you know, you're actually paying people to annotate data for you, but in a very massively kind of distributed way. A lot of these, that's a kind of commercial model for that. A lot of these kind of using, you know, people to do this sort of relies on some people feeling that there's some benefit for doing this. So these citizen science projects, it's the volunteers on that are actually helping some specific scientific study, for example. But there's a whole kind of area around incentivizing people to actually do this. Or you could do what those CAPTCHAs do, where it's kind of make people have to do that to get through to the next stage of signing up for a service. So it's there's many different ways that can be thought about how to actually incentivize people to do that.
I have a question. So in terms of the current slide you are showing at the moment, 21, you mentioned you are interested in partnering with companies. What kind of partnership do you think of?
So so it's interesting. We've been, you know, in discussions with a number of different companies around doing these kind of projects. And what CeADAR can offer is we have the machine learning and AI expertise, the technical expertise in this. And, you know, we're more and more developing our more specific Earth observation expertise. But as I mentioned, a lot of the general machine learning techniques can be applied to Earth observation data. So we can do a lot very quickly in this space. But what we are interested in with partnering with the company will know what their pain points are, the solutions they want to achieve, what the sort of business case, what they're trying to do in their particular area. So whereas CeADAR, we can help with the technical expertise to actually develop these techniques and help with the deployment of these techniques. It's the use case or the business case of how Earth observation data and AI could be used for benefit in a particular industry that would we'd like to work with industries that have ideas in that space, and then we can help them on the technical side of that thing. So I think these kind of collaborations where we work from our technical expertise combined with the business and use case kind of expertise of someone from the industry is where these are efficient. And sorry, just to give a few examples. So, you know, there's a lot of traditional maybe uses of Earth observation data for sort of smart agriculture and other areas than that, and we're working in many of those. But there's some alternative ways that can be used. So, for example, insurance companies looking at things like subsidence of buildings, for example, from radar data from satellites. You know, that's the use case that can be used maybe for risk modeling. So there's a lot of potential applications out there that I think there's a huge competitive advantage potential for companies, and we can help them with the technical aspects of it. So I think if anyone has any further questions that they don't want to say now, maybe please feel free to get in touch with me or any of the CeADAR team. We're really happy to discuss any further aspects of what I was talking about today, or any of the other projects we're working on in the Earth observation space.
I don't know if I have time to ask another question.
Sure, please go ahead.
Yeah, actually, you mentioned the AI-ready EO training data set, which will be started in June, something like that.
Mm-hmm.
So, is it announced somewhere? What is the plan of this project? How long it takes time? What kind of the data are you going to, generate? Something like that. I assume actually you want to generate some sort of standard training data set for this kind of research topics. So how we can get a little bit more information about this project and everything about it?
Sure. So, well, we're sort of still in the initial stages of developing the project scope and so on. It's due to start around in June. And once the project starts, a key aspect of this project is involvement and involving the community in AI, the community in Earth observation, and generally interested people in this kind of area. So once the project starts in June, we'll be building a website, we'll have a blog, we'll have communication mechanisms to build up this community of interested stakeholders and people on this project. And the key idea in this project is that in a lot of other areas where AI is applied, there are these standardized data sets in standardized formats that can be combined together that really make it easy for AI and machine learning practitioners and Earth observation, in these other areas to use these techniques and to really develop better technology. Whereas in the Earth observation space, it's kind of a little bit behind in that. So this project is really about involving the community of researchers, of interested companies to develop these standards for the Earth observation type data. So the project will develop a number of different training data sets, but it's really about developing a specification that will be put out there. It's all going to be open source. We're going to be developing Python libraries and tools as well to help people use these new specifications. So it's a real community effort. There'll be a lot more information once we start the project, which should be mid-June. Fingers crossed with the current situation.
And what kind of the project it should be? I mean, it is supported by a specific agency or something like that. What is the length of project, etc.? Is it possible to know information about these things?
Yeah, so it's a project by the European Space Agency that they ourselves and iCheck applied, put in an application for this project. But the project originated with the European Space Agency. It's going to be, the initial phase is about 12 months long. Once we start the project, there'll be a lot more information about there. But a key aspect of that is really involving these stakeholders and different AI and Earth observation communities, from researchers to practitioners. So there's a huge communications piece and involvement piece around that. But that will all start in June.
Great, thank you.
I have a follow-up question to that.
Sure.
You mentioned the European Space Agency in there. Are you mostly expecting to be using Sentinel data from the Copernicus program for this?
Sorry, for the Ario project specifically.
Yeah.
Yes, I think the focus, will be on using using data from European Space Agency sources for that. But the idea, it's developing open source specifications and standards for how these data sets are defined, different data formats, different types of labeling, and all those kind of intricacies of that. So the idea is that it's a general format that can be applied across all different kinds of Earth observation data. Now, the sort of sample data sets and demonstration data sets that we're going to be building initially in this project will more than likely be using data from Sentinel and so on. But it's not restricted to a particular source of data.
Thank you.
Just finally, I see Philip has asked something by message here. So about GDPR challenges. So intrusive of privacy, satellite data. Yeah, that's an interesting kind of thing. The legalities of, as these sensors improve and the data quality and the frequency maybe of capturing the data on particular parts of the Earth. I mean, there's a satellite could be going over me right now, actually taking a photo through this skylight window of me right now. Is that a intrusion into my privacy? I would say it is, but I think there's a whole range of issues around there in terms of personal privacy and so on around that. That's not really something that we have a huge amount of expertise in, but it's definitely something we keep an eye on, kind of developments in that as this data is used more and more.